Hello and welcome to our course project presentation. This project is called as Experiments with OpenAI Gym's Bipedal Walker V2 environment. Let me begin by telling you about our environment and the approach we took. So our environment is built on top of the box 2D physics engine. Our input observation space is of 24 dimensions. So the approach we took was first to go over existing uh, algorithms that are dominant in the OpenAI leaderboard. We found that the DDPG algorithm, the TD3 algorithm, and the A3C algorithm were dominant. We took TD3 algorithm as our baseline. Quick update about the TD3 algorithm: it has CLIP double Q learning, which is a minimum estimation over double Q learning. It also has the TD3 updates are of lower frequency than the vanilla updates. Also, TD3 has a smoothing regularization strategy. Further, we experimented a lot with the A3C algorithm, which was introduced by DeepMind and has obsoleted DQN since its introduction. The A3C stands for Advantageous Asynchronous Actor Critique algorithm. A quick overview of the A3C algorithm. In the A3C, there are multiple agents which interact with the environment, and all of its experience is learned by a global network. In case of the A3C, the global network has separate fully connected layers and a different gradient step to update them.
To take you through the experiments that we ran, we chose, instead of taking the TD3 as a baseline, with what we discussed, we took A3C MLP because it was much faster. Now TD3 also did not converge to 300 the way we wanted it to. As you can see, the A3C converged, not only converged, but converged much faster within 40-50 episodes. So during training, we could tell if something was going to work, if something wasn't going to work. So the approach that we took was we did some further analysis into the kinds of games that OpenAI provides, and we found that Atari games, actually, since the dimensional space is much higher, they used convolutional networks. But I mean, our dimensions weren't that high, but we still wanted to experiment with convolutional networks and see if we could actually improve the efficiency of the A3C algorithm even further. But however, we found that though there was enough capacity to reach the optimal reward for the algorithm, we actually did not hit it consistently, which we attributed to different initializations. We thought that maybe certain initializations were being overfit, which is why we then tried the dropout. We took the same model with the convolutional layers, and we added about a 0.5 dropout to each layer. And we found that by doing so, we reduced the complexity so much that we actually did not hit 300 in the average reward per episode. That being said, we figured that we would keep the convolutional the model without the dropout, just the convolutional layers, and we wanted to change the activation function. Previously, what was being used was a leaky ReLU activation function, and since at below zero in the negative space, it's actually a linear function. What we wanted to do was introduce an ELU activation function, which is actually a more complex function in the negative space. And we actually found that even with the convolutional approach, we actually could reach capacity and converge at the maximum reward point. This was actually in comparison to the initial, though we didn't actually beat the initial baseline, which converged much faster. We were able to take our convolutional baseline and make it much better. Actually, I mean, you could compare it to the Google baseline without the convolutional, with the fully connected network layers. In conclusion, we used the A3C model as a baseline. We took the fully connected networks, we made convolutional networks, and we tested out the different parameters like dropout. We changed the activation function, and we just wanted to see if we could actually, if not beat, build a similar model that reaches Google's results that they've published. Yeah, and so that's it for our project. Thank you.